In last lecture, I was discussing about SMAW process and I have completed the SMAW process. There we discussed detail about SMAW process. That was a arc welding process actually. Today also I will discuss about another arc welding process. SMAW process generally a consumable types of electrodes generally used. Today whatever the welding process I will discuss, that is generally non-consumable types of electrode here used to generate the arc. Here a non-consumable electrode tungsten is used. This welding technique name is GTAW process, or that full form of GTAW process is gas tungsten arc welding process. This is also simply it is known as TIG welding process, that is tungsten inert gas welding process. Why it is called tungsten inert gas arc welding process? Because here a tungsten electrode is used and a inert gas is used to shielding the molten pool as well as electrode from atmospheric contamination. That is why it is called that shielding gas is generally is a inert gas. That is why it is called tungsten inert gas arc welding process also. Now I will discuss in details about this welding process. Generally whatever the flow of a lecture were there in previous lecture, like in SMAW, here will be also the similar flow. There will be introduction of this welding process, then principle of this welding process, then this setup of this process, and if there will be any categories or welding parameters, important parameters of this welding process, then that I will discuss, and at the end I will discuss the advantages, disadvantages and application. So, this is the generally flow of the lecture about whatever the welding techniques I will discuss in this course. This will be the flow of our lecture. So, first of all I will discuss about introduction of GTAW process. Gas tungsten arc welding process was initially called as heli arc. Why it was called as heli arc? Because here used a shielding gas, that was helium gas, and here to generate the heat here was used a electric arc. So, combination of this helium gas as a shielding medium and the electric arc. So, from helium's heli was taken and from arc from electric arc was taken, and combining this combinedly this was called as generally heli arc. It was invented generally in 1939, it is long back actually. Here generally what happens here, heat for fusion is generated from an arc between a non-consumable electrode and base metal. This non-consumable electrode is tungsten electrode. It is not consumed during welding operation. It remains as it is. It generally it is not consuming or melting of that electrode is taken place. That is why it is called non-consumable electrode. Through this generally only current is flowing and it is responsible for generating the arc. So, here generally it is not act as a filler wire. Generally here an inert gas is used as a shielding medium for the arc and the molten whirlpool. Here one thing you should keep it in mind, this inert gas or this shielding medium not only protect this molten pool from the atmospheric contamination, at high temperature it also protect the electrode, that means this tungsten electrode from atmospheric contamination. Generally at higher temperature tungsten is very reactive with oxygen. That is why what happens, the tungsten gets readily oxide if it come in contact with oxygen, especially if the temperature is little bit higher side. Then here generally another things you keep it in mind, here either argon gas as a inert gas is used or helium as a inert gas generally used, or combination of this can be used as a inert gas in this welding process. Now, this is the TIG welding setup, or we can say GTAW welding setup. Here the equipment used for TIG welding, here it is showing. Here use a inert gas supply cylinder. It can be argon gas, it can be helium gas, or it can be a mixture of argon helium gas. Here is used a power source. This is the power source. This inert gas hose is connected to this torch and it's go to this nozzle. Here you see this is called nozzle and this is called tungsten electrode. Tungsten electrode. So, through this generally this inert gas pass through this torch handle to this nozzle and it cover this its flow around the arc. So, it generally cover this molten pool arc as well as electrode also, what I have already discussed previously. So, here you see this is generally power source. This power source can be a AC power source or DC power source. This power source, one terminal connected to the workpiece, another terminal connected to the torch. Generally torch, actually what happens, torch there is a contact tube is there. This contact tube here, this is here it is more clearly shown. Here you see this is generally called contact tube. With this contact tube, this power supply cable is connected. So, another terminal is connected to this workpiece. Here you can easily see this is shielding gas, this is generally called tungsten electrode, and you see this is here arc is generated. Here sometimes generally if flare material is required, this flare material is supplied separately. This is called flare wire or flare rod, which is generally used during welding operation. This is act as a consumable material, this flare wire. It does not carry the current, but it acts as a consumable material. It generally melt by the arc, and what happens is melted, and it is melted and it is deposited over the weld pool. So, this is generally detail all setup of this welding process. It has generally a power source, a welding torch, a tungsten electrode, and a gas supply system are there. This is the actually practical view of this gas tungsten arc welding setup. Here you see this in left hand, this is flare wire, and in right hand this is a torch. Here you see there is a control switch at the thumb. So, generally by pushing these things we can control the flow of gas flow rate and other things we can control by pushing or pulling this knob, we can control the gas flow rate. Okay. Now, you see, now we will discuss more details about this TIG welding setups. Here it is the original or actual setup of this TIG welding process. This is called a torch. In this torch there is a nozzle. You see this is nozzle here, here I am showing this is this nozzle size also depending upon the gas flow rate, this nozzle size generally varied. Here I am showing. Here you see this is generally tungsten electrode. This is tungsten electrode, how it's look like. This tungsten electrode size also varying. It is generally varying, it's varying from depending upon the requirement. Generally it's varying its size, its maximum size within a range of around 4.5 millimeter diameter. And you see this is generally called contact tube. That means through this generally this tungsten electrode is passed, and from this contact tube connected to the power source through connecting cable. So, through this generally this current pass through this contact tube to electrode. Here one thing you should keep it in mind, this electrode can be pure tungsten or it can be generally some alloy tungsten. That means here this pure tungsten, here you should know what is the difference between pure tungsten and alloy tungsten. Pure tungsten generally temperature resistance are comparatively lesser than alloy tungsten. Alloy tungsten can carry more temperature than pure tungsten. Apart from this thing, it has high resistance to contamination also in alloy tungsten. But what happens in some cases, what it is called alloy tungsten is preferable, in some cases pure tungsten also preferable. Where it is, that I will discuss in details in here. Electrode material could be pure tungsten, especially this can be pure tungsten if the DCSP is used. DCSP means direct current electrode negative, if the electrode negative terminal is used. Because if the electrode negative terminal is used, then what happens, you can see from here itself, if the electrode is negative terminal, if it is negative terminal and if it is positive terminal, then what happens, bombardment of electron will be taken place to workpiece. So, what happens here, less heat will be generated in case of tungsten electrode, in case of this tungsten electrode generally the less heat input around 30%, that what I have already discussed, and here generally 75% heat will be so here as here less heat will be generated, that is why generally pure tungsten we can use in case of DCSP. Because what happens, there are no need to alloy the what it is called tungsten material. That is why pure tungsten is easily be used if the state polarity is there, because less heat is generated. So, what happens, less chance of contamination of electrode are there, or less chance of melting of the electrode will be there. That is why DCEN, generally for DCEN we can use pure tungsten. But generally alloyed or we can say generally alloyed or coating electrode, like generally thoriated tungsten or zirconated tungsten is used in AC or DC as well as DC current. This thoriated alloy tungsten or zirconated alloy tungsten we can use both AC and DC. Why? Because generally if we use DC EP also we can use this thing. DCEN is DCEN is possible. Apart from DCEN, here we can use DC EP also, because this alloyed tungsten electrode generally high thermal resistance power. That is why what happens, due to this high thermal resistance we can use this alloyed tungsten electrode. And in AC, why it can be used? In AC, generally AC is a combination of direct polarity, that means DC EP as well as DCEN. So, what happens here generally compared to state polarity or DCEN, in case of AC generally due to this combination of DC EP and DCEN, in case of AC generally more heat is generated. So, what happens, as here more heat is generated, it is better to use alloyed tungsten electrode here. So that is why generally in case of AC as well as DC, there the DC we can use this what it is called this alloyed tungsten electrode. Alloyed tungsten electrode, what I have already told, alloyed tungsten electrode possesses high current carrying capacity, high resistance to contamination. It is generally high resistance to contamination also. Thoria or zirconia coating, or this thoria or zirconia coating also produce a steadier arc due to their higher thermoionic emissivity compared to pure tungsten electrode. So, whatever the arc we get from pure tungsten, generally if we use alloyed tungsten electrode, there we can get better or more steadier types of arc. Apart from this thing, here one thing you should keep in mind, generally this thoriated or pure generally tungsten, pure tungsten or this alloy tungsten have some specific application also. When welding of copper, like in nitrogen atmosphere, once we do welding of copper in nitrogen atmosphere, then this alloy tungsten electrode are preferred. This you should keep it in mind. Alloy tungsten electrode are preferred, because nitrogen generally attacks pure tungsten very easily. That means once it is higher temperature or at molten state, near to molten state, generally nitrogen attack the pure tungsten. That is why if we use alloy tungsten over there, then what happens, chances of this attack will be less, that means reaction will be less. So, what happens, that is why for copper welding especially, this is some special case, once we go for doing welding of copper material by using nitrogen gas, then we should use this alloyed what it is called alloyed tungsten electrode. Whereas for aluminum it is preferable to use pure tungsten compared to alloyed tungsten electrode. That also you should keep it in mind. Now we will discuss what is the principle of this operation. Principle of this operation here generally, that means first the detail of the principle of operation is, first of all we have to switch on the power source, that means welding current, then water and inert gas supply are turned on, first of all we have to do. Then the arc is struck between workpiece and electrode, either two different process, either by touching the electrode with scrap material or scrap material or using a high frequency unit. So, these two methods generally used to generate the arc between electrode and workpiece, that is by touching electrode with scrap metal or using some high frequency unit. So, in the first method generally, that means touching the electrode with scrap material, what it do generally, in the first method arc is initially struck on a metal piece or a tungsten piece, that is scrap metal, and then broken by increasing the arc length. Then this arc is extinguished by generally increasing the arc length between workpiece and electrode, then generally the arc extinguished. So, this arc stack generally should repeat 2 to 3 times to warm up the electrode. Then the arc is struck between pre-clean job to be welded. That means, so after warm up of the electrode, that means 2 to 3 times in scrap material, then we have to do the actual welding operation. So, that then we have to stack our arc after 2 to 3 times in scrap material, we have to start our arc, start the welding arc to pre-cleaned. Actually, this should be cleaned, pre-cleaned job to be welded. There we have to start the arc. Then if we do in this way, that means before starting the actual welding, if we warm up the electrode to 2 to 3 times in a scrap material, then what happens? This method avoid breaking of electrode tip, job contamination and tungsten loss. So, these are the things, if we do it like this, then we can eliminate these things, that means job contamination, breaking of electrode tip and tungsten loss. In the second method, that what I have already discussed in details when I was discussing a starting of arc, that is a high frequency unit. High frequency unit consists of what I have already discussed. It consists of a high voltage and low current equipment. This high voltage and low current which is passes through very high frequency. That is why a high frequency circuit is generally superimposed on the welding current here. So, when the electrode tip reaches within 3 to 2 millimeter from the job or workpiece, generally a spark jump across the air gap between the electrode and the job, what I have discussed already. Then due to this spark jump across the air gap between electrode and job, generally the arc air path get ionized and arc is established. This is another path, another way, or this is another way generally to start the arc. This is the principle of this TIG welding operation. Now, we will go for what are the different sequence of this welding process, that also we should know, because how the welding start and how it should finish and what should be the sequences of this process, that also you should know, that I am showing here. In case of manual GTAW process, generally these are the sequence we should follow. First of all, this weld paddle is developed due to arc action to the workpiece and the electrode. That means, whatever due to arc action, generally here a weld paddle is developed. So, once the weld paddle is developed, then what happens? This welding torch is moved back. So, in second sequence, generally in next step we should move the welding torch back. This should make say angle around 15 degree with this vertical axis. Then if filler material is required, we have to supply filler material. This filler material also position should be like this. This also should make say angle around 15 degree with horizontal surface, and this should put in front of this torch, and this filler rod is moved ahead and filler material is generally added to the weld paddle. This filler material generally continuously here you see supply to the weld paddle. So in this way it's move with this torch in front of this torch and it continuously melt and supply filler material to the weld paddle. At the end, when the welding is completed, then what we have to do? Then we have to first remove this filler wire from there. So first remove the filler wire from there, then we have to extinguish the arc. So here one thing you should keep it in mind, the shielding gas is allowed to impinge on the solidifying weld pool for a few seconds even after the extinguishing of arc. This thing you should keep it in mind. That means the shielding gas supply should be there even after extinguishing of arc for few seconds. Then your welding will be, weld paddle will be fully eliminated from oxidation or whatever the generally contamination from atmospheric contamination. So that is why here this shielding gas is allowed to impinge on the solidifying weld pool for a few seconds even after extinguishing of the arc. That you should keep it in mind. Now here these are the main operating variable is welding current, welding voltage, welding speed and shielding gas. I have already discussed about this thing at the end of the physics of welding topics. Again there are some specific or special generally purpose, some special types of polarity and other things is used. That is why I will discuss about this welding current here, but rest of the thing generally arc voltage, welding speed, shielding gas, that what I have already discussed in details in that topics itself. So, I will not discuss that things here, because whatever the function of that thing over there, that is the general function of that things here also. Here also this current also same function, but here generally some specific purpose it is used here, that is why I will discuss here about welding currents in detail here. So, generally here one thing you keep it in mind, here either AC current or DC current is used. What I have already told that means direct current or alternating current power source can be used here. Here one thing you should keep it in mind, as it is a non-consumable types of electrode, that is why always keep it in mind here DCEN is preferable, because state polarity is preferable, because if it is a state polarity that you know, then less it will be generated in electrode, because as it is non-consumable, so less it should generate over there. So, what happens here, less chance of melting of that electrode also will be there, and heat loss also will be less. That is why DCAN is preferable. Now, if we want for steel matter, especially for steel matter, if we want high penetration, then helium gas is generally used. That is why here one thing I have written, deep penetration and fast welding speed with DCEN, especially with helium gas. Now, here another things we should keep it in mind, that means for welding aluminum, once we go for welding aluminum, there is generally use alternating current. Why alternating current is used? That I will discuss in this details in subsequent slide. Here generally one thing you keep it in mind, due to this AC current, generally why alternating current is required. Generally this aluminum is a very reactive types of material. Generally once you just keep it in open weather or atmosphere, you can see immediately over the surface of this aluminum there generates some oxide layer, that you can see. So, what happens immediately it is oxidized, that means aluminum is such a material. So, what happens, this oxide is a refractory types of oxide. In this oxide whatever its form in case of aluminum with oxygen, that is generally Al2O3, it has a melting point around 2072 degrees centigrade, whereas pure aluminum generally has a temperature only 660 degrees centigrade, 660.3 degrees centigrade actually. So, you see from here itself you can see this oxide on its form, then its temperature rise around 3-4 times more than its original aluminum. So, generally during welding operation, if this is included inside the weld metal, then it creates some inclusion in the weld, that is a defect actually, it creates defect. So, generally we should avoid this alumina or refractory oxide, this is a very tenacious oxide that we should avoid. This we can avoid, or this we can remove once we use AC current in case of aluminum welding, aluminum or magnesium types of material generally, there these types of oxide formation, chances of this oxide formation is high. So, that is why generally here AC current is used. Why AC current is used? Generally if we use AC current, in AC current, AC generally is a combination of DCEP plus DCEN, that means it is a combination, one half is electrode positive, another half is generally electrode negative is there. This electrode positive polarity generally here is very helpful to clean this alumina, or you can say this refractory oxide, aluminum oxide. That is why generally this ECP, but if we continuously use this DCEP, that means DCEP if you continuously use, then what happens, your electrode will be warm up or heated more. So, what happens, because in case of DCEP generally 70% heat is generated in electrode, and so what happens, if the continuously if it is connected to DCEP, then what happens, there is a chance of what it is called warm up this electrode and melting of that electrode is there. That is why generally what happens, but DCEP have a effect of on this oxide cleaning. That is why if you continuously use this DCEP over there, then there is a chance of tungsten electrode melting and it deposited over the what it is called welding material. Then there is a chance of what it is called inclusion, tungsten inclusion inside the weld material. To avoid this thing, if we use AC, then in one portion of the cycle will be DCEP, that time generally this cleaning action will be taken place, in other portion generally it will be DCEN, that time generally this tungsten electrode will be cooled down. So, what happens, so here generally continuously warming up of this electrode will not be there. So, chances of that thing what it is called melting of electrode inclusion will be less over there. So, that is why generally if we use AC current, then in one cycle we will get cleaning action, which generally eliminate this aluminum oxide. In other polarity case, generally we can get lowering the temperature in electrode as well as deep penetration, because more heat will be generated generally in DCEN, more heat is generated in workpiece, and bombardment is of electron also is taken place in workpiece. So that is why generally there is a chance of more penetration also. So once you use AC or aluminum welding, then generally we can get this cleaning action as well as high penetration. Here one thing you should keep it in mind, for aluminum welding generally argon shielding gas is preferable. Why argon shielding gas is preferable? Generally argon in argon atmosphere generally this cleaning action is occurred. Generally that is the cleaning action, or this is sometimes called a spattering effect. Generally this spattering effect generally occurs in case of argon atmosphere. It is not occur generally or generally in case of helium atmosphere. It is not good, that means helium atmosphere is not good this spattering effect or cleaning action. That is why argon gas you should use during aluminum welding, and you should use alternating current. So spattering does not generally take place with helium, here it is written already. In case of manual GTAW, generally you should keep it in mind, argon as a helium gas generally is more preferable or generally used. Now what I have already told you, generally polarity in this currents almost every time it is DCEN is used. Why it is used, that I have already told you. Generally if you use DCEN, then generally less chance of warm up of the electrode and melting of the electrode is there, because less heat it will be generated in the electrode and more heat will be generated to the workpiece. So generally for deeper penetration is achieved with DCEN then DCEP. But DCEP generally have limited application for steel material also. Generally if the steel material whose thickness is less, or for generally some sheet metal types of material, generally this DCEP is also preferable. Because why it is preferable? Because in case of thinner material we want less heat to generate in workpiece, because if more heat will be generated, there is a chance of melt through this workpiece. To avoid this melt through, generally DCEP is also used in case of sheet metal for TIG welding process. But DCEP, what I have told you, DCEP is preferable for cathodic cleaning, especially for magnesium and aluminum alloy. This is what I have told you. Now here cathodic cleaning action I will discuss here in details. Generally here cathodic cleaning action is taken place with alternating power source, and here one thing you keep it in mind, with AC argon shielding gas is used for welding aluminum or magnesium, because once we use AC current over there, then and argon gas is there, then there will be better arc starting, better cleaning action and superior weld quality. Now what happens during cleaning action, that also you should know. Once what I have already told you, once this aluminum or magnesium exposed to atmosphere, then immediately some oxide layer is formed over the surface of the aluminum. Then this oxide generally once it include inside the weld material, then it creates some defect. This oxide can be broken by using DCEP polarity. What happens due to this DCEP? DCEP means, here you see, DCEP means this is negative, this is positive, this means electrode is positive, this is negative. So if it is DCEP, then what happens, electron will flow from electrode to workpiece direction. So due to this electron flow, or you can say ion coming to workpiece, so here generally positive ion is will be attracted here, and generally electron will flow upward direction. Due to this flow of electron and ion, generally what happens, once it is DCEP, or you see it is also called generally reverse polarity. If it is reverse polarity, then what happens, this aluminum, that means that refractory oxide broken up. So this refractory oxide broken up, and once it broken up, then it generally float over the surface of the molten pool. So generally then due to this DCEP polarity, this thing happen. So once it is broken up, and generally they float upon the molten metal. So then this thing, that means this broken off alumina, or you can see this broken off refractory oxide no longer interfere with the welding process. So then it will not be able to create any defect inside the weld metal. So this thing generally happen once we use DCEP as a what it's called DCEP as a polarity. So, that is why you should keep it in mind for aluminum, magnesium types of material, generally alternating current is used. Here you can use DCEP continuously, but if you use DCEP continuously, then there is a chances of that thing what I have already discussed, warm up of the electrode and melting of the electrode. Apart from this thing, you can get less penetration. So, to get this high penetration and less warm up of this electrode, here generally it is preferable AC current. So, that is why you keep it in mind for aluminum, magnesium, alternating current is very much preferable over here. So, another thing here you should keep it in mind, once you go for aluminum welding with AC current, there you should use argon as a shielding gas. Why? Because argon has suitable for a spattering effect than aluminum than helium inert gas. Now, this is the categories of TIG welding process. Now, we will discuss what are the different categories of TIG welding process. Generally, this TIG welding can be done manually or it can be mechanized also. That is why depending upon this mechanism, it can be categorized in two different categories. One is called manual TIG welding process. Manual TIG welding, what I have already discussed during categories of different welding process. Manual means here both speed of the welding as well as filler wire deposition is controlled manually. So, generally here no mechanized system is there. So, that is why generally it is called manual TIG welding process. Manual TIG welding process means torch is operated by one hand and filler wire is also operated by another hand. So, here both the things is controlled manually, then this is called manual TIG welding process. And in case of mechanized TIG welding process, here generally this torch movement, that means welding speed is controlled by some mechanized system, as well as this filler wire. This filler wire also is controlled by some mechanized system. This mechanized system means from some roller, it generally continuously feed to the molten pool through some feed roller actually. This is generally called feed roller. This feed roller generally controlled by some mechanized system. So, what happens by this, generally we can control both what is called control both filler wire deposition as well as speed of the welding torch by some mechanized system, then it is called mechanized GTAW process. Here you see, so this automatic TIG welding or this mechanized TIG welding, here the welding torch is automatically guided and this filler material, if there is use, it is also fed automatically from some reel. This process is attractive for large production run, as it is automatic process, that is why attractive for large production run. Here instead of AC current, here DC current is preferable, and DC current with DCEN is used instead of AC current. Here we can do the welding from a thickness varying from 0.2 millimeter to 10 millimeter. Now, these are the different other process variants. Generally, what happens to increase the productivity of TIG welding process, there are some other variation of this welding process are there. What is this variation? What are these variation? This variation can be cold filler wire TIG welding, that is called cold wire TIG welding, and to increase the productivity you can use hot wire TIG welding. Apart from this hot wire TIG welding, here you can supply hot wire as well as some oscillation of the wire by some oscillation system, you can supply the wire. By this also you can increase the productivity, and another process variant is orbital TIG welding. So, now I will discuss in details about this welding process in subsequent slide. First of all, I will discuss about cold wire TIG. Here cold wire TIG, it is a conventional GTAW process. Here whatever the filler wire is supplied or introduced into the leading edge of the weld paddle is supplied at atmospheric temperature. That means the temperature of the filler wire is before supplying to the leading edge of the electrode or arc. Generally this temperature is within the temperature is atmospheric temperature, that means at cool condition. So, whatever the energy required for melting of the filler wire, generally whatever the energy required to melt this filler wire, that is generally taken from this arc. So, as this filler wire's melting temperature is or energy is taking from arc, that is why here generally heat losses, you can say some sort of heat energy reduces. So due to this generally here efficiency of the process decreases, because heat is taken away by this filler wire to melt it and deposit it. So that is why generally less heat is supplied to the edge of the whirlpool. So what happens, less forceful arc will be there, so less penetration and other things will be there. So here generally efficiency is less. So here generally it is reducing the efficiency of the process. Now in case of hot wire, what happens, this instead of supplying this filler wire at room temperature, here this filler wire supply at a temperature which is closer to its melting point temperature by some heating mechanism. Here this mechanism is showing here, then it will be very clear to you. This is the hot wire GTAW process or setup. Here you see this is the arc which is generated by this power source, and you see this is generally wire feeding mechanism, from where generally this wire is continuously fed to this job. Here with this contact tube, there here you see with this contact tube and this workpiece, in between a power source is used, that is called wire heating power source. This power source generally use heat up this filler wire, to heat up this filler wire by electrical resistance heating. Because what happens, by this heating power source, it generally due to the resistance of this what it is called filler wire, it is warm up by this wire heating power source. So what happens, this heating generally here you see how it is heating, this power source generally connected with this what it is called a contact tube and what is called workpiece. So in between whatever the filler wire are there, that filler wire heat by electrical resistance heating. So what happens, this resistance heating generally rise the temperature of that filler wire, and once it closer to melting point temperature of this filler wire, then what happens, it supplied to the well puddle, or we can say whirlpool. So what happens here, generally less heat will be required from the, or less heat will be taken from the arc to melt this filler wire. So what happens here, you can say that whatever the arc force or arc energy is there, that generally directly supplied to the molten pool. So here generally more forceful arc and more forceful arc we can get. So what happens, due to these things, by this welding process generally we can increase deposition rate as well as penetration. So what happens, for this reason this welding process or these techniques can be 2 to 3 times faster than the cold wire TIG welding process. Because what happens here, we can increase both penetration as well as what it is called deposition rate. So that is why a sentence is written here, a 2 to 3 times faster travel speed is realized by this welding process. Here generally graph is, or we can say from this figure itself we can see how the means deposition rate varying with cold wire TIG welding process and hot wire TIG welding process. Here hot wire TIG welding process. Here you see with variation of arc, this is generally represent with variation of arc how the filler wire deposition rate, that means kg per hour, how it is varying. With variation arc, it has observed that let's I am just considering for a particular then it will be very clear to you. Let's for a particular power, for a particular power general for a particular power, let's for a particular power at around 7 kilowatt power. For 7 kilowatt power, if we use a cold wire, then we can get a filler material deposition rate that is around 1.5 kg per hour. Whereas for the same power, if we use a hot wire TIG welding techniques, there we can get a what it is called deposition rate is around 7 kg per hour. Further, if we want to increase the deposition rate, if we just oscillate this filler wire by some oscillation technique, then oscillation mechanism, then further we can increase the filler wire deposition rate, which is around 8 kg per hour. That means further also we can increase by increasing the hot wire filler wire oscillation by providing the hot wire oscillation by some oscillation mechanism. So, in this way one things we can observe, we can get around 4 to 5 times more deposition rate compared to cold wire in case of hot wire techniques. And if we want further increase of deposition rate, we can oscillate that hot wire by some oscillation system. Okay. This is the feel of how the means deposition rate. So, due to this high deposition rate, we can increase the speed of the welding also. That is speed of the, we can increase the speed of the welding 2 to 3 times more than the cold wire welding techniques. Now, these hot wire TIG welding techniques have huge application. It has generally application, it's apply in high quality fabrication in stainless steel. It is used in aluminum, copper and nickel alloy. Generally welding in reactive and refractory metals such as titanium, tantalum, zirconium, it has wide application. This process, generally this hot wire process is extensively used in nuclear and aerospace industries and in the construction and maintenance of chemical and cryogenic process plant and pipe work. This hot wire techniques is widely. Now, we will go for orbital types of TIG welding techniques. Orbital TIG means it is generally used for circular section. Generally, it is used in nuclear, pharmaceutical, semiconductor and food industry for installation of pipe work. So, where generally circular section is there, generally it has wide application. It has especially used where high quality standard are required, this TIG welding, because TIG welding is itself is a very high quality welding techniques. It generally give very high quality weld. That is why most of the time I am telling this high quality purpose generally where is there generally these types of technique is used. Especially this equipment is used for tube and tube plate welding. That means where there is circular section is there. Now, depending upon this size of the tube or this size of the tube and size of the welding head, generally what happens, these welding techniques we can do from inside tube or from outside of the tube also. So, that is also written here, depending on the tube diameter and size of the welding head, this system may be operate from inside or outside of the tube. So, this is generally here you can see that this is a pipe which is welded by this orbital TIG welding process. Here generally you see this orbital TIG welding head is set up generally outside. Generally this what it is called, this pipe generally rotated by some rotating mechanism, here you see by some rotating mechanism, and here generally arc is generated between this workpiece and electrode. Then what happens, we can do the we can join these two pipes separately. So, we can do due to the rotation of this pipe and the supply of arc heat, generally we can join this pipe. Here it is showing like this. Now, joint design in case of TIG welding also we should know what are the different joint we can do by this welding process, that also we should know. Here generally most of the joint we can made by this TIG welding process, like it can be used in butt, T, lap, corner as well as edge wall can be edge joint. Also here a wall can be welded by this TIG welding process. A square groove generally butt joint is used for a smaller thickness plate. So, generally for a plate thickness lower than around 4.5 millimeter, there cannot be require any edge preparation. So, for lower thickness plate, edge preparation means a square butt. That means here no V angle is required. So, without edge preparation, that is called a square groove. A square groove that you know already, I have already discussed about this thing. This is called a square groove. For lower thickness material, no bevel angle or V angle is required, but a single V angle is required once the plate thickness varying from 4.8 to 9.6 millimeter. That means within a range of around 10 millimeter thickness plate, there is required a single bevel angle. This single bevel angle or included angle ranges is around 60 degree. Generally, a double V groove generally is required for this TIG welding process. If the plate thickness exceeds 12.5 millimeter thickness, then double V edge preparation or double sided edge preparation is more preferable. That means at both sides you have to make the edge preparation. You have to make the edge preparation. So, from this side you have to do the welding, similarly from other side also you have to do the welding. So, once this plate thickness is exceed greater than 12.5 millimeter thick, generally this types of S preparation is required over there. Now, we will discuss what is the advantage of this welding process, drawback of this welding process and application. This welding techniques has huge advantage because this more metal and metal alloy can be welded by using this welding process than any other processes. Here what I have already discussed, here generally a shielding gas medium generally used to protect the weld pool as well as electrode. So, that is why as here no flux is used, so there is no chance of flux entrapment inside the weld puddle. Here generally high quality and precision welding operation, this is a very high quality and precision welding operation technique. It is suitable for thin material, as thin as 0.1 to 5 millimeter thick section also we can weld by this welding process. It is a here generally pinpoint control are there. This process can weld in all position, this can be this positional welding, that means all position welding you can do by using this welding process. Here this SMAW, whatever the spark and other thing are there, here generally that types of spark or spatter is marginally less you can say. Here no smoke or fume, that means whatever the smoke fume you observe in case of what it is called SMAW process, here that thing is not there. Here no flux or slag also is not there because flux or slag is not used here. So, these are the advantages of this welding process. Now, what is the drawback of this limitation of this welding process? Here one thing you keep it in mind, here generally lower filler material deposition rate, comparatively lower than MIG welding process. Generally here metal deposition is less, and as here is used tungsten electrode, so there is a chance of this tungsten melt and deposited over the molten metal. So, there is a chance of tungsten inclusion is there. Here one thing you keep it in mind, here generally very good hand and eye coordination skill is required. Here you can see these types of pinpoint skill is required, generally pinpoint concentration is required to do this welding operation. Here you see, so that good hand eye coordination skill is very much essential in this welding operation. Here generally there can be a brighter UV ray than other process. In this process whatever the UV ray here in arc are there, that can be brighter than other process. Here slower travel speed than other process like MIG welding process. Here generally equipment cost are higher than SMAW. In SMAW process whatever the equipment cost are there, here generally more than that cost. Now, application of this welding process, what I have already told you, this is generally very much suitable for reactive and refractory metal. What I have already told you what is reactive material and refractory material. Reactive material titanium, zirconium, then refractory material generally tantalum, molybdenum, these are the refractory material metal. This is very difficult to weld, which can be welded by this welding process. It has wide application in this reactive and refractory material. It is highly used in carbon, alloy steel, carbon and alloy steel, stainless steel, heat resistance alloy, aluminum alloy, magnesium alloy, copper alloy and nickel alloy also. Welding stainless steel, here one thing you keep it in mind, welding stainless steel, argon is recommended for manual welding of a thickness up to 12 mm. That means if the plate thickness within a range of 12 mm, then argon gas is sufficient for what it is called stainless steel welding. But if it exceed this 12.5 millimeter thickness of a stainless steel plate, then what happens, it is more preferable to use argon helium mixture gas or simply helium gas is better. So, over 12 millimeter thickness it is better to use helium as a shielding gas for stainless steel. Another things also you should keep it in mind, if we use aluminum or magnesium types of welding, their alternating current is preferable, what I have already told, and what happens, and there should use argon as a shielding gas, because generally if we use AC with argon gas for aluminum welding, it provide better arc starting, better cleaning action, superior weld quality than helium as shielding gas. It has wide application in atomic energy, aircraft, chemical, instrument industry. It is also used in rocket motor chamber fabrication in launch vehicles. So, it has wide application in here, that means rocket motor chamber fabrication purpose. So, you see it has very high advantage process and it has very high application also. Now, here just I am showing some welding parameter for GTAW process, then you can get some idea that what should be the range of welding current required for doing steel welding, aluminum welding, or it is called copper welding, what should be the tungsten size, what should be the filler wire rod size, and what should be the range of flow rate of shielding gas is required. That is for the purpose of some knowledge. Here I am showing some parameter for different types of material for a thickness of 6 millimeter thick plate. That means, for 6 millimeter thick plate for different types of metal, what are the process parameter is required. Here one thing you can see, if we use aluminum for 6 millimeter thick plate, here the current range varying from 200 to 350, and here generally current type is AC, and here the tungsten diameter is within a range of 4.5 millimeter. And filler rod, if we use this filler rod size is varying from 3 to 5 millimeter depending upon this variation of current. It is a filler rod diameter, and here argon gas flow rate is 9 liter per minute. That means, per minute 9 liter of gas should flow, then what happens, you can get a very good quality welding. That means, there will not be atmospheric contamination and it will be almost defect free types of welding process, welded joint. Then for magnesium, here you see current is varying from this for 6 millimeter thick plate. Here tungsten diameter is 2.5 millimeter, filler rod diameter is 4 millimeter, and argon gas flow rate is 10 liter per minute. If you go for here also AC current is preferable, what I have already told you. Then for copper, here you see 250 to 735 current range is required. Here direct current state polarity. Why state polarity? Because DC-EN is used, because DC-EN is a state polarity, then electrode will be less heated. That is why generally DC state polarity is preferable, or DC we can say DC-EN is preferable. Then DC-EN is used, and here tungsten diameter is 3 millimeter, filler rod diameter 3, and gas flow rate is this 7 liter per minute. If it is mild steel, low alloy steel, or stainless steel for 6 millimeter, here current range vary from 250 to 350, and here also DCSP, because definitely in case of this welding process, TIG welding process, generally DCSP is preferable, what I have already told. And as it is what it is called 6 millimeter thick plate and steel plate, that is why here tungsten electrode diameter is 3 millimeter, here filler wire diameter can be 3 to 4 millimeter, and gas flow rate, that is argon gas flow rate is 7 liter per minute. If it is cast iron, then also it is given. In case of cast iron, both AC or DC state polarity we can use. Here generally 3 millimeter diameter tungsten, 5 millimeter filler wire, and 8 liter per minute generally what it is called argon gas flow rate is required to get good weld. So, this all about TIG welding process or GTAW welding process. Generally in next lecture I will discuss you about another arc welding process, that is called GMAW process, or that is simply it is also called MIG welding process, that is called metal inert gas welding technique, that I will discuss in details in next lecture.